4:15, so let's go ahead and start the colloquium. And it's a pleasure to have one of our own speaking this week, Mike Zaletel. I will quickly introduce Mike, whom I've known for a while. He was an undergraduate at Deep Springs College and then Harvard University, and then a graduate student at Berkeley in our own Department of Physics. He was a postdoc at Microsoft Research and then went to Princeton as faculty for 1 year before coming back to Berkeley. And as the Thomas and Allison Schneider Chair in Physics, among his many awards for his career stage, especially, it's quite impressive, is the Macmillan Award given to an outstanding condensed matter physicist. And I would like to say maybe 1 or 2 words about his work, although I think you'll get a better feel of it from watching the talk. So I think the part that will come out in today's talk is his work on understanding some of the most challenging materials out there because of correlations or topology or other aspects, and understanding what experiments are trying to tell us. And the other aspect of his work is in computation, but it's basically in extending computation to deal with problems that are currently inaccessible, and also to learn something about the structure of many body states. So for example, one of his, probably his best known work from graduate school, which did not involve his PhD advisor at all, was on understanding the structure of topological states through a new concept from computer science, basically from tensor networks. So I don't know if that's going to come out as much in the talk today, but it is another very impressive thrust of his work. So with that, let me hand over to Professor Zaletel.
Great, thanks, Joel. It's good to be here, though I wish it was in person, but maybe another time. So today I'm going to be talking about charged Skermions and superconductivity. So just an outline of the talk. So I want to start out with the introduction to what Skermions are. They were a type of particle first proposed by Tony Skermi in the context of nuclear physics back in the 60s, but subsequently have found lots of applications in condensed matter physics and quantum materials more generally. Then I'm going to be talking about a potential application of Skermions as a route to high temperature superconductivity, in particular in this very interesting material a lot of my group and others at Berkeley are studying, which is twisted bilayer graphene. And then finally, I'm going to talk about a collaboration with an experimental group at Princeton, Ali Yazdani, about how to use scanning tunneling microscopy to actually image the presence of these Skermions, and we think that might be a way to either prove or, in all likelihood, falsify this idea of the Skermion superconductivity. Okay, so what was the inspiration for Tony Skermi thinking about this idea? Really, it's an idea that a lot of us find inspiring that goes back to the ideas of Lord Kelvin that perhaps particles are actually topological defects like vortices in underlying continuous medium. So the example of this that we've all probably seen day to day is if you have air, you can generate a vortex in the air, and due to the circulation theorem, vorticity is actually conserved. So once you make one of these vortices, it can propagate as a stable object. So Kelvin first proposed that perhaps, this was before they had really figured out how the periodic table worked. Perhaps the different atoms that we encounter are different types of knots and vortices in some underlying continuous medium. Maybe not air, but in the ether itself. So this sort of idea I find very beautiful, that maybe there's just one continuous medium, a field, and all the complexity of the material world might just come from the different ways this field can be knotted. This kind of idea has actually found lots of applications in condensed matter physics, from classical statistical physics of liquid crystals, for instance, where you can have vortices in some liquid crystal orientation, more exotic realizations like the fractional quasi-particles of the quantum Hall effect, or in various types of frustrated magnetism studied by James Analytis and others, where you can have a magnetic order where there's defects in it, and then the centers of these defects can carry interesting magnetic properties. But the realization that I'm going to talk about today was actually first proposed by Tony Skermi in the 60s. And the situation he was considering were defects in the Pion fields. So his equivalent of the air that the vortices were instead field configurations of pions. And the structure of those fields is they're actually composed of 4 real numbers corresponding to different ways of creating different flavors of pions. So that's this field N here, but it satisfied a constraint, which is that you have this 4-component field, but its length was fixed to be 1. So because of that constraint, the field takes values in a 3-dimensional sphere. Fields of this form are often called nonlinear sigma models. So Skermi was interested in considering configurations of this field, which can be interpreted as particles, and particles should have a finite amount of energy. So we should restrict our attention to configurations of the field where far away it just takes on some constant limiting value, which you can think of as the vacuum. So when you do this, rather than thinking of the domain of the function as being real space, you could think of it as being a sphere, actually, because we can identify all the points at infinity as one point. And therefore, the different field configurations you can think of as maps from the 3-sphere to the 3-sphere. So as soon as you see an object like this, mathematically, you should get interested. Because if you talk about what is the space of all maps from the 3-sphere to the 3-sphere, that has an interesting topological invariant called the homotopy group. So what it tells you is that there's different classes of functions from the sphere to the sphere. Those classes are labeled by integers, and you can't continuously deform from one to the other. So Tony's original idea was perhaps that this integer invariant of fields actually corresponded to the number of particles, in particular nucleons, in the system. So working in 3 dimensions is a little bit difficult to visualize. So let's actually develop some pictures for what these field configurations look like if we step down a dimension. So now, instead of thinking about 3 space, I have 2 space, the XY plane, and my target space that my field lives in instead is just the 2-sphere. So now I can think of field configurations as just assigning a 2-dimensional vector to each point in space. We still have that the homotopy groups are Z, and I've drawn here 2 interesting configurations, 2 non-trivial ones that correspond to a homotopy invariant or 1 or -1, and you can think of it as like a hedgehog. So something I can think of the space you start with a sphere and the final space is a sphere. I can draw the field configuration as a hairy decorated sphere. And we have this non-trivial field configuration where at each point in space, the field points outwards. And there's no way to continuously deform that to a configuration where the field is constant, or what we can think of as the antiparticle here, where at each point in space, it points inward. Okay. So these are examples of 2 different Skermion configurations shown here. Now, if rather than thinking of it as from the sphere, I map it down to real space, and the typical figures they take are shown here. Far away, the field configuration is all down, and then at the very center, it reorients upwards to the opposite pole. Okay, so this topological invariant is a global property, but there's a nice convenient formula for how to measure it from local data, and this will come back later. It turns out if you measure this particular combination of gradients of the field, n dot n cross n, this gives what we call the topological density. You can measure that locally, and if you then integrate that over all space, it's guaranteed to give you an integer invariant, which measures which of these classes you're in. So as long as the field changes continuously, this is an invariant, and so that topological invariance we might interpret as the stability of a particular particle being there or not. And where is the particle? Well, it's just the location where the field orients in the opposite direction. So Skermi's idea was that nucleons, the protons and neutrons, are actually Skermions in the Pion field. So it's a very beautiful idea. But there's an aspect of this which Kelvin couldn't have really anticipated, which is that if we're going to claim that nucleons are these defects in the Pion field, we need to explain a very important property of the nucleons, which is that they're fermions. But that's a very perplexing thing. The pions are bosons. We have a purely bosonic field. How could it be that a defect in something purely bosonic could end up giving you a particle which behaves as a fermion? So there was a beautiful series of work understanding this, starting with Skermi, but it was really only resolved into the 60s and 70s. The first example I'm aware of where this was shown was in the context of even one lower dimension, where Skermions just take the form of domain walls. So this is work of Coleman and others. And there they were able to very concretely show in terms of the field theory why domain walls, these solitons in the field configurations could actually obey fermionic statistics if you chose the right Lagrangian for them. The application to 3 dimensions, where Skermi was originally interested, and I believe the emergence of the fermionic statistics was really only understood by Witten in the 80s. And what he found is that there's an interesting topological term in the Lagrangian, so basically some Berry phase effect, from which you can see that when these Skermions moved around each other, they actually had fermionic exchange statistics. So this is very cool. I think a really beautiful idea that fermions can actually emerge out of non-local textures in a bosonic field. So high energy theorists shouldn't be able to have all the fun. Since then, lots of condensed matter work has tried to figure out whether there's condensed matter systems rather than pion fields where we could also realize Skermions. The most obvious example is just to think about a ferromagnet. So if you have a ferromagnetic order in a thin film, because the film's thin, you can think of space as just being two-dimensional. And the order parameter describes at what direction each point in space the magnetism points. That exactly gives a map from two-dimensional space into a sphere, which is the setting in which we can get Skermions. So there's beautiful work from Ramesh's group, for instance, in finding materials that actually show this. To get them to appear in practice, what you usually need is a particular type of magnetic perturbation in the system called the DM interaction. It arises from spin-orbit coupling, and it prefers for the spins to have a finite value of s cross s. Basically, it prefers the spins sort of rotate around at different points in space. So people have discovered materials with these terms. There's an example of it in iron monolayers shown on the left. What this picture is showing is this is the plane of two-dimensional space, just taking a picture of the ferromagnetic order. And the color indicates the orientation of the order in the XY plane and the intensity from black to white, whether it points towards the north or south pole. So you can see there's this effective crystal that develops where at each black point, it points at the north pole, and then the spin orientation rotates around it. That's actually just a flattened out Skermion. So what's happening is that in this system, there's a particular interaction which prefers there to be a crystal of these Skermions localized on a triangular lattice. Very cool. There's other systems where rather than forming a crystal, they'll just kind of randomly get tied to different defects. That's what's shown here. And then they're allowed to move just like particles would, and very much in alignment with Kelvin's original vision. So this is cool, and there's lots of potential, for instance, spintronic applications where you can write and manipulate and move these Skermions around. But it's a little bit different than Tony Skermi's original vision. Skermi was really interested that maybe what you thought were the basic particles, the nucleons, could be understood really as defects in the bosonic field. So in condensed matter, we might ask an equivalent version of that. Could it be that the electron itself could be understood as a Skermion in, for instance, a magnetic order? Sounds kind of crazy because, of course, it's the electrons ultimately that are making up the system, but we've learned that there are, in fact, systems that we can understand this way. So what was the first example? It's actually the physics of the quantum Hall effect that was worked out back in the 1990s. So what's the physical setting? We're going to start out with a two-dimensional sheet of material. It could be graphene, for instance, that Feng Wang is working on, but originally these were just semiconductor films. So the electrons are confined to move in a thin sheet. And then you apply a very, very strong magnetic field to it on the scale of several Tesla, and electrons tend to enter into these cyclotron orbits just because of the Lorentz force. So one of the very famous results on this, going back to von Klitzing, is that if you measure the electrical properties of this, for instance, the resistivity and the Hall conductance, it shows a very beautiful pattern as a function of the magnetic field once you reach low enough temperatures. And in particular, if you measure the Hall conductance, one finds that the Hall conductance takes on quantized values in units of E²/h, where it's E²/h times some integer nu. So this here is an experimental trace. The x-axis is the magnetic field. The y-axis is showing the Hall conductance, and measured in E²/h, you'll see it takes these discrete steps where it's always an integer times E²/h. Okay, so what does this have to do with Skermions? Well, it comes into the spin physics of the problem. So in this TUDEG, the electrons, in addition to where they are, they still have their spin degree of freedom. And it turns out, as I'll explain, that we actually think that the quantum Hall effect is itself an example of a ferromagnet. And whenever you have a ferromagnet in 2D, you can have Skermions. So how do I see this from the data? Well, it's interesting to note here what integers actually arise in the sequence. So if you look at the locations of the plateaus, at the highest magnetic fields, you see both odd and even integers, 1, 2, 3, 4, 5. And then at the lower magnetic fields, only the even integers apply, 6, 8, 10, etc. So where does this come from? Well, we need to dive into a little bit how the quantum Hall effect works. And the first thing we need to consider is just what are the single particle energies available to electrons in a magnetic field. There's a beautiful calculation of Landau, which shows that rather than having quadratic dispersion or even relativistic dispersion in a magnetic field, the energy of electrons become perfectly quantized into discrete levels called Landau levels. These Landau levels are usually indexed by an integer, here 0, 1, 2. And then within one of these Landau levels, there's actually a massive extensive degeneracy. Basically, there's one single particle state per flux quanta. So we have this set of Landau levels, and then in addition, it's actually spin degenerate because you could have put electrons into each Landau level, spin up or spin down. So the basic picture for where the integer quantum Hall effect comes from is whenever your Fermi level lies in a gap between Landau levels, a gap opens, and the Hall conductance is exactly measuring just how many of the Landau levels are filled below you. So that would explain the integer jumps. So this also explains, at first glance, it would seem, it explains the odd-even effect. So, because you're applying a magnetic field to this system, there's a Zeeman splitting, which slightly splits the energy between the up and down electrons. It turns out that in a material like gallium arsenide, the splitting is actually really small. It's like 0.2 Kelvin per Tesla. So it's there, but it's actually much smaller than the cyclotron gap between these Landau levels. Okay, so maybe that would explain why you get the odd-even effect. At very low magnetic fields, the Zeeman energy is small, and so you'd expect that you need to go to super low temperature in order to actually reserve odd integers, because you only see it when the chemical potential lies in a gap. Whereas if you're filling an even number, then your Fermi level lies in these big cyclotron gaps and would be a much more robust phenomenon. Okay, that's a reasonable explanation, but it turns out the numbers don't work. So that would predict that the odd integer Hall effect would show up for temperatures below the Zeeman energy. But the Zeeman energy is really small in this system, whereas the integer quantum Hall effect is seen at tens or even like 100 Kelvin. What's in fact seen is that it seems that the energy scale governing the odd integer quantum Hall effect is actually E squared over the typical distance between particles, which is the magnetic length, which is orders of magnitude larger than the Zeeman energy. So the fact that the energy scale is going E squared over distance tells you that it's actually coming from the Coulomb repulsion between the electrons, not the single particle effect. So the picture for what's happening is that even in the absence of a Zeeman field, the quantum Hall effect would actually like to spontaneously break the spin rotational symmetry and have all the electrons go in with some particular fixed spin orientation because of the Coulomb interaction. So this is an example of spontaneous symmetry breaking. And the typical scale then is set by the interactions which drive the spontaneous symmetry breaking rather than the Zeeman energy. Okay, so then the Zeeman field in this picture is actually just a very small perturbation and isn't really that important for the physics of the system. Okay, so that's to say that the quantum Hall effect, even though there's a strong magnetic field, properly should really be understood as a symmetry breaking phase and hence a ferromagnet. So once we have a ferromagnet, we can now consider what happens if you put Skermions into the orientation of the magnetic moment. And the really cool thing in the quantum Hall effect that we don't have in some of the other materials considered is that it turns out that whenever you put a Skermion in this system, not only does it carry a magnetic moment, it always also carries an electrical charge. And there's a cool formula for this result. So you might remember that the way to figure out the density of Skermions in the system is this particular invariant here, this n cross n. And it turns out that the electrical density is directly proportional to the Skermion density, with a constant of proportionality, which is basically just the Hall conductance. So if you're pointed in a positive magnetic field, the Hall conductance has units of basically 1, and then you'd find a Skermion carries charge 1, whereas if the magnetic field points in the opposite direction, the Hall conductance is -1, and then it will carry a charge -1. So we can give a little bit of picture for where this comes from. Why do Skermions end up carrying physical electrical charge? And it comes from the physics of the Hall effect. So let's imagine we just fix a Skermion in the system. So it's a texture and the spins we've shown here. And then let's add one additional electron to the system, like a probe test electron, and see what sort of forces it experiences as it moves through the system in the background of the Skermion. Well, because of the ferromagnetic interaction, as it moves through the Skermion, its own spin wants to cant to follow the local magnetization in the system. So I'll keep track of that canting on the right here. The spin can be represented as a point in the Bloch sphere. And therefore, as it moves around in space, its orientation, the spin space, moves around some path depending on how you move through the Skermion. Now, here's where the interesting physics of Berry phases come in. We know that when a quantum mechanical spin traces out some area, it picks up a Berry phase in proportion to the area enclosed. That Berry phase is just like how when an electron moves in the presence of the magnetic field, it picks up an Aharonov-Bohm Berry phase. And now, because of the physics of the Hall response tells you that whenever the system experiences an additional magnetic field, the Hall conductivity tells you that that induces some additional electrical charge there. So d rho dB is equal to the Hall response. But as far as this test electron is concerned, it doesn't know whether the Berry phase it's picking up is from the magnetic field or the Berry phase of its spin moving around. And so those two effects just add together. But the Berry phase that it's picking up due to the spin is actually just exactly equal through this geometric factor here to the Skermion density there. So that's the basic physics of why Skermions through the Hall conductance end up carrying charge. So if you integrate this formula over one full Skermion, you find that the Skermions carry charge 1 or -1, depending on whether it's a Skermion or anti-Skermion. So as far as I know, this is the only condensed matter system where it's really been proven that charges enter into the form of topological defects, just like Kelvin first envisioned. Okay, so we're going to use this formula later on. The physical electrical charge is equal to the Hall conductance, which I've heard here called C, or the Chern number, times the number of Skermions in the system. This isn't just an abstract theory. It's actually been seen in a series of beautiful experiments in the 90s. The way they do it is they're able to use NMR to measure the magnetization in the system. That's going to be the y-axis here. And the x-axis here is the density of electrons in the two-dimensional electron gas. So they start out at a density of 1, which is this ferromagnetic integer quantum Hall effect that would just give a perfectly pristine ferromagnet. And then they find that as they add electrons to the system to change the density, they can see that the magnetic moment rapidly decreases. Now, if the electrons were just entering into the form of what we naively think of as an electron, each electron added would reduce the spin by exactly the g factor of 2 of the electron. But that's not what's seen. It turns out that each electron you add, or each charge 1 that you add, instead seems to reduce the magnetic moment more with a g factor of like 20. And the reason that's happening is when you add a charge, it actually comes in as a Skermion. The Skermions have a core where a bunch of the spins reverse, and so that carries a large magnetic moment, and the system rapidly depolarizes as you dope the density. So that's the proof that the charges really are Skermions here. Okay, so with that background on Skermions, that was physics that was figured out in the 90s, and there's cool experimental evidence for it. What we're sort of thinking about now is, okay, if you could have that your charge carriers are Skermions, what useful properties might that have? In particular, for instance, might give a way to realize superconductivity at temperature scales potentially much larger than the usual conventional mechanisms. So this is a collaboration I'll be talking about, led by postdoc Shubayu and Nick Boltink at Berkeley, as well as my collaborators at Harvard. Okay, so the question I want to ask is, could we have superconductivity mediated by objects which are Skermions rather than electrons? So to answer that, we should start out and just give a super brief review of how superconductivity works. Well, the basic physics of superconductivity is that you need that for some reason, the electrons in your system prefer to pair up, they're glued together and they form a molecule that we call a Cooper pair. It's kind of surprising that should happen because of course the electrons repel each other, but there's various theories, for instance, that phonons can effectively mediate a force between electrons, which cause a very weak attraction between them, which can, roughly speaking, overcome the Coulomb repulsion. So once you pair together these electrons into a Cooper pair, if you put two fermions together, that's a boson, so the Cooper pairs are charged to bosons. And if you have a boson, the natural thing it can do at low temperature is bosocondense. And at a crude level, we can understand superconductivity is basically a bosocondensate of these Cooper pairs. So for this to happen, there's two things. The first step is we need the pairing glue, the thing that ties the electrons together into a pair. And then second, to drive the bosocondensation, these Cooper pairs need to have a kinetic energy like p²/2m, because we know bosocondensation is driven by the desire for the system to minimize its energy by putting all the bosons in the same zero momentum state. Okay, so we need both of those. So the question is, might Skermions if those are your charged carriers, like we've seen in the quantum Hall effect, might they be good in some sense for either the pairing glue or the kinetic energy, which leads to condensation? Now, at first glance, at least in the quantum Hall realization, it might seem like the answer is definitely no for the following reason. So he said, to get a Bose-Einstein condensate, we need p squared over 2m. We need some dispersion. But if you have particles in a charged magnetic field, their kinetic energy is frustrated because they're forced into these cyclotron orbits. And in fact, if you look at the energy momentum relation for charged particles in a magnetic field, you get these Landau levels, which are completely flat. So there's no kinetic energy at all. So if condensation is driven by kinetic energy, this is clearly bad for superconductivity. So as far as I know, there's no reason to think that with the quantum Hall effect alone, even if you have Skermions, that there'd be a way to see superconductivity there. So magnetic field bad. Okay, so what's the solution we're going to propose to this to try and get superconductivity? Well, to start, I'm just going to pose a kind of crazy sounding model that naively, at least, would seem like it would be quite hard to realize in the laboratory. And then later in the talk, I'll come back into how you actually do this. And in fact, experiments here in Berkeley may already have the material in hand which does this. So what's the setup I want to consider? I'm basically going to take two copies of the quantum Hall effect. So you could think of it as two sheets of graphene separated vertically on top of each other. That's not so hard to do. People could easily do that in an experiment. But the tricky thing I'm going to do is that one of the sheets, I'm going to have the magnetic field come out of the plane, and the other sheet, I'm going to have the magnetic field point in the opposite direction. So in practice, that'd be hard. You'd need like a constant sheet of monopoles between the two of them to realize it. Okay, but I'll come back to that. Okay, so when you now look at the single particle states, you basically get two copies of the quantum Hall effect. So you'd have a series of Landau levels for one layer and a series of Landau levels for the other. And the density of electrons I'm going to focus on is when you fill two of the Landau levels, one Landau level in the top layer and one Landau level in the bottom layer. Okay, so now individually, both of them still carry spin. And so you'll have ferromagnetism in the top layer and ferromagnetism in the bottom layer. There's one more ingredient I'm going to need, which is that I want the magnetic moments of the two subsystems to actually talk together in some way. And I'll assume that the interaction between the magnetic moment in the two layers is antiferromagnetic, and the strength of this antiferromagnetic term is going to be captured by this factor J. This might seem sort of ad hoc, but it's actually very natural to get antiferromagnetic interactions when you have bilayers, because it arises naturally within perturbation theory whenever you allow a little bit of tunneling between them. Okay. Now, let me just add a little more notation. So to keep track of the ferromagnetism in the system, I'm going to need to describe what is the magnetic moment in the top layer, which I'll call N+, and also the magnetic moment in the bottom layer, which I'll call N-. Okay, so where do Skermions come in? Well, the most naive thing you could do, because I have two copies of the ferromagnet, is I could just put a Skermion into the ferromagnetic order only of the top layer. But that's not going to be very energetically feasible in this system because of this antiferromagnetic interaction. Wherever you have a Skermion, at the core of the Skermion, the spins end up pointing in the opposite direction. So now when you look at, you have a pristine sheet below and a sheet with a Skermion above, at the core there, you violate the antiferromagnetic interaction, you're going to pay an energy penalty J, which drives up the cost of a single Skermion. So what can we do that has lower energy than this? Well, suppose we instead put a Skermion in the top layer and an anti-Skermion in the bottom layer. That's the thing that has the opposite homotopy invariant. So the way we relate these two is exactly to get an anti-Skermion, you just flip the orientation of the ferromagnetism everywhere. So instead of pointing out of the sphere everywhere, it points into the sphere everywhere. Now, because the field configurations are now equal and opposite in the two layers, my antiferromagnetic interaction is perfectly happy, and so the J term is satisfied. Okay, but what's interesting about this object, a Skermion on the top and an anti-Skermion on the bottom? Well, the key rule I had is that the electrical charge was equal to the Skermion charge times the Hall conductance. And my basic construct was that I was going to flip the magnetic field orientation between these two layers. The Hall conductance is also flipped between the top and the bottom layer. So in the top layer, I have the total charge is 1 times 1. And in the bottom layer, 2 wrongs make a right. And the electrical charge is also 1. So this bound state of a Skermion and an anti-Skermion is in fact a charge 2 boson if it was a stable thing. So that's interesting because as soon as I have charge 2 bosons, that's the sort of thing which could superconduct. Okay, but to show that this thing would actually occur in practice, there was the two ingredients I needed that need to pair and that it would want to condense. So first, let's discuss the pairing. Why is it favorable for these two Skermions, a Skermion and an anti-Skermion, to sit on top of each other? The dominant term in the Hamiltonian doesn't want this. That's the Coulomb repulsion. If both objects carry charge E, they want to repel just to the 1 over R. On the other hand, I said that putting a Skermion and an anti-Skermion made the anti-ferromagnetism J happy. So we need to figure out what wins. And Shubayu is the one who really worked this out in great detail. But the basic physics of it is as follows. If you have a Skermion, it's an object that can be spread out over a large radius R. That tends not to penalize the elastic energy, but it reduces the Coulomb energy because you're just spreading out charge and making it a big diffuse object. Okay, so if the Skermion has radius R and you bring two of them on top of each other, the Coulomb repulsion you pay is spread out over R, so it's no bigger than about 1 over R, the units of the Coulomb interaction. On the other hand, we said that when you look at the attraction between the Skermion and anti-Skermion, there's this anti-ferromagnetic interaction J, which doesn't want them to be not on top of each other because that would unalign the spins. So you find that the attraction is negative times the area and the repulsion goes over as 1 over R. So as long as you make the Skermions big enough, it's guaranteed that the attraction wins out and the things will form a bound state. So this gives one of the only ways I know where for an arbitrarily small attractive interaction, you can actually overcome Coulomb repulsion and generate a stable bound state. So this is going to be the basic mechanism for why Skermions are really good for superconductivity. So the other thing I need to explain is where the dispersion would come from that leads to boson condensation. And there's a kind of cool argument here that comes from the way the magnetic field works. So what I want to show is that despite the fact that the electrons themselves have no kinetic energy, they're just in Landau levels, which have no kinetic energy, nevertheless, the pair of Skermions does actually have kinetic energy. So to see this, let's imagine that you start with a Skermion pair and boost it up to velocity v so that both of them are moving. So these are two charged objects and the two different planes experience opposite magnetic fields. So they're going to experience a Lorentz force, which is equal and opposite. So as they start moving like this, the Lorentz force starts pulling them apart. Now, the reason they don't just keep flying apart is because there's this attractive interaction between them, which binds them together. And so it will end up in some equilibrium state where the binding force balances the Lorentz force at some particular fixed separation between them. But the fact that they've been drawn apart is bad energetically because they've lost some of their binding energy by having to pulled apart. So if you just analyze this, you find that the energy of the Skermion pair as a function of its velocity ends up taking the form mv squared, just like a regular kinetic energy, where this mass that emerges has nothing to do with the electron mass, but is actually set purely by the Coulomb interaction and this anti-ferromagnetic term J. So this gives us a way to have a dispersion in completely flat bands, which I think is a very interesting mechanism. So with that, we actually have the two ingredients we need for superconductivity. Big Skermions can cause pairing despite Coulomb repulsion, and they disperse despite the fact that the bands are flat. When you put those together, you can get a Bose-Einstein condensate. Shubayu and others did a lot of detailed calculations to try and figure out, well, in this mechanism, what's actually the scale of superconductivity you'd get, what's the critical temperature, and it turns out it's basically set by J times the density of Skermions in the system, which is quite different than when you get for the conventional theory of superconductivity, like BCS theory. You'd have a very different temperature scale for superconductivity. So this is why you basically decoupled the system from having the usual constraints on the largest temperatures that superconductivity can arise at. Let me quickly say, this sounds like a very hand-waving argument. We've really actually done extremely detailed numerical calculations of this. So there's a long history of being able to do calculations to predict the effect of interactions in quantum Hall physics. They're difficult, but you can do them, and that was a lot of what my graduate work was on. We can do the same thing here where we just take two copies of the quantum Hall effect with the two different magnetic fields, and we can apply some of the same numerical tools. And Shubayu and another postdoc, Matteo at Stanford, did very involved calculations on exactly the model I described with the full Coulomb repulsion, et cetera. And they did in fact find that very simple model is a superconductor. Okay, but can it be realized? It sounded super exotic. We needed to realize a two-layer system with opposite magnetic fields. This is where we're going to make use of a lot of the interesting insights that Joel, for instance, has been a leader on. It was realized by Duncan Haldane, for instance, and this is what the 2016 Nobel Prize was awarded for, is that the basic physics of the quantum Hall effect, that you can get Hall conductance, can actually be realized in models of electrons hopping through a periodic potential without having to apply an external magnetic field at all. So you just need to cook up some models where when electrons hop through this lattice, they accumulate some complex phases, some Berry phases, but these effects are just naturally there in most materials we look at. And subsequently, there's been lots of interesting work actually discovering materials that effectively behave like quantum Hall states in the absence of a magnetic field. Okay, but we need to find a kind of peculiar one where half the electrons see a magnetic field one way and half the electrons see a magnetic field the other way. And it turns out that one of the materials, which is, there's been a tremendous number of people working on this experimentally over the last 3 years since it was discovered at MIT, is so-called magic angle graphene. So the properties of this were first really explored experimentally by Pablo's group at MIT. And the basic setup of it is you take one sheet of graphene, and then we're going to put it on top of another sheet of graphene. But before you do that, you twist one relative to the other by a very small angle. You could think on the order of 1 degree. So that means that the carbon atoms in the graphene don't sit perfectly on top of each other, but instead, because you have an interference pattern between their two crystal lattices, you get the so-called moire pattern, where in some regions they fit nicely on top of each other, whereas in other regions they anti-align. And as you move through space, you oscillate through these at a length scale that depends on the relative orientation between them. Okay, so you can see a picture of here. This is exaggerated slightly. At the angles which are usually used in experiment, the degree is something like 1. And if you ask what is the period of the unit cell, it would actually have something like 10,000 carbon atoms in it. So it's a much longer length scale than the original carbon lattice. So this is a pretty interesting system. When electrons move through it, they see two lattices. They see, of course, the original graphene one, but they also see this moire interference pattern as another lattice on top of it. And that's at a much longer length scale, maybe 100 times larger, 15 nanometers or so. So it's a little bit like realizing a cold atoms experiment where we've artificially made this superlattice through this interference phenomena, and then electrons will move through it as a periodic potential, and that completely changes what their band structure looks like. So I kind of think of this as a way that, cold atom physics was originally tried to do solid state physics in cold atomic lattices. Now we're going to try and simulate cold atomic lattices in solid state systems. Now, the interesting thing when you do this in graphene is you get a super weird band structure. So what's plotted on the right here is just what is the energy required for an electron moving through the system when it has a particular momentum. The momentum is the x-axis here. So this is the dispersion relation. And whereas in graphene, you get relativistic dispersion, it turns out that there's a special value of the relative twist orientation here where the energy momentum dispersion almost becomes completely flat. It's as if you put an electron into the system, it would barely move due to some destructive interference phenomena. So we call this the emergence of two flat bands. So you can see the band structure here. And the really interesting thing is when you dig into what the structure of these two bands is, it turns out that one of them has wave functions that look just as if it was in a positive magnetic field, and the other band has wave functions that look like it's in a negative magnetic field. So it turns out that the band structure of twisted bilayer graphene already actually realizes this interesting weird bilayer that I claimed might have superconductivity. Okay. Now there's one detail here. I'm showing the two of the bands, but graphene, the electrons also carry spin degree of freedom and also a Valley degree of freedom. I've come back here. So there's actually many copies of this, and that's going to be important because when I discuss superconductivity, I needed to have that each of these layers also had a spin, and indeed they will in this example here. So I'll come back to that. So is superconductivity seen in magic angle graphene? Yes, that was the huge experimental revelation back in 2018. The sort of experiment they do is using some nearby gates. They can control the electron density, that's the x-axis, and then they measure the conductance, and they find that when, two interesting things. One, when the electron density takes on certain values where there's an integer number of electrons per unit cell of this Moiré superlattice, they find that the system actually seems to spontaneously break a symmetry and become an insulator that you wouldn't expect from band theory. So they call this a Mott insulator. And then it turns out that when you change the electron density slightly away from the symmetry broken state, they see superconductivity arise. And superconductivity had never been seen in graphene alone. It's really special to having these two graphene sheets with a relative twist between them. So this got a lot of people thinking about why does superconductivity occur in this magic angle system. And really, this was actually the motivation for our thinking about Skermions. So what does this have to do with the quantum Hall effect? Well, we said that the band structure kind of looks like two copies. You can think of it as the two layers. Both of them have some effective versions of Landau levels. And our interpretation of these Mott insulators, or these symmetry broken states, is just when you put a number of electrons into the system such that you fill one Landau level in the top layer and one Landau level in the bottom layer. And when you do so, you need to pick a particular orientation in the spin space, and that's the symmetry breaking, which leads to an insulating sort of ferromagnet. Okay, so at a high level, it turns out that magic angle graphene already realizes the physics we need. There's these symmetry broken ferromagnetic insulators. Whenever you have an insulator ferromagnet in 2D, it could have Skermions. Because they appear effectively like Landau levels, these Skermions end up carrying charge too. And so the hypothesis that a lot of my work has been focusing on over the last year or so has been trying to figure out whether this could really be the explanation for superconductivity in twisted bilayer graphene. Now, when you plug in the sort of computations that Shubai did using the actual microscopics of this model, we in fact predict that the superconductivity you get would have critical temperatures on the order of a Kelvin, which is what's seen in experiment. So it's actually feasible. We can do pretty interesting numerical calculations on this. This picture here is not actually from my group. This is from the group at Oxford. And it's a picture showing what happens when you inject charge into one of these insulators, and he finds that the charge distributes in this blob, which is exactly consistent with these Skermions. So we think this is fairly realistic. Okay, so but this is just a crazy theory proposal. Is it what's actually happening? Well, clearly we want to do experiments and find out. There's been a lot of interesting recent work showing that the superconductivity in twisted bilayer graphene does seem to be unconventional. There's pretty clear evidence at this point that Coulomb interactions play a really strong role. There seems to be violations of some of the usual expectations of conventional or BCS superconductivity. So there's room for this Skermion mechanism to potentially work, but we don't yet have any direct evidence that really the Skermions are there and what's driving it. And so that's another big part of my work that I want to talk about. What experiments might we do to show that this very exotic theory for superconductivity might actually be what's happening. So what we'd like ideally is a way to do an experiment where we could literally see that when you inject an electron into the system, it makes a Skermion in the ferromagnetic order. Now, if you want to image the properties of electron at the nanoscale, the best tool to do it, or at least one of the best, are the sort of experiments that Mike Cromie does here, and that's scanning tunneling microscopy. It lets you image the wave function of electrons at the scale of single atoms. So how is this imaging going to work to see Skermions? There's one complication here that I've been trying to avoid, but I need to mention it now, which is when I talked about the symmetry breaking in the case of the quantum Hall effect, the spin was literally the electron spin, like which way its magnetic moment was pointing. It turns out in the magic angle graphene realization, the spin that's realized is a little bit different. Rather than the spin degree of freedom, it's what we call the valley degree of freedom. So when you look at the band structure of graphene, it turns out that there's two distinct minima at which electrons have low energy. So we call these two valley. And so when you look at the low energy physics of this system, there's actually two different momenta it could arise at, and we label those momentum as K and K prime. So the spin that's going to be important for the ferromagnetism is not actually, the familiar electron spin. That two-dimensional degree of freedom is actually going to be which valley the electrons are in. So when we talk about Skermions and magic angle graphene, it's actually going to be Skermions between the K and the K prime valley. And as we'll see, that has very important consequences for whether you could hope to literally see these with an STM, and I'll argue that the answer is yes. Okay, so this brings us to the last part of the talk, which is what experiments we're going to try and do to detect these valley Skermions. And we've sort of gotten halfway there in this collaboration with Ali Yazdani. You know, my contribution to this was just as a lowly theorist. They were the ones doing really amazing experiments. Xiaomeng gave the condensed matter seminar last week. This is the group at Princeton, and this actually goes back to a collaboration I started with them back when I was there. So what's the system they're looking at? It's a little bit simpler. As I said, this is only halfway to trying to either falsify or proof or demonstrate Skermions and twisted bilayer graphene. Here, they're only looking at a single monolayer of graphene, so just a single sheet. And it's going to be realized in the same way that the quantum Hall effect is. They're going to apply a very strong magnetic field to monolayer graphene. And the claim is that when they then do STM, they're able to see Skermions. Okay, so let's unpack how. Okay, so we're looking at the quantum Hall effect in graphene, and there's two differences compared to those early experiments in the 90s. One of them comes from the fact that as electrons move through graphene, they actually experience a relativistic or Dirac-like dispersion relation. And the consequence of that is that the Landau levels not just occur for positive energies, you also get Landau levels at lower energy, negative energies coming from the Dirac-C. Okay, but we still get perfectly flat Landau levels, just now indexed by any integer z rather than a positive integer. The other difference is when we go to look at the degeneracy of these Landau levels. So just like before, electrons carry spin. So each Landau level has a copy from up and copy from down. But as we said, at low energies, electrons also could occur at different momenta, k and k prime. So we also have a sort of pseudo spin corresponding to the valley. So all in all, each Landau level actually has 4 copies. We call these 4 together the isospin. And you know, just as before, you can then talk about whether there's spontaneous symmetry breaking in this enlarged 4-component space rather than the spinful 2-component space. And indeed, it's found that there is. So whereas at the level of non-interacting band theory, you'd only predict quantized Hall effects, where the Hall conductance is a multiple of 4 coming from filling these 4-fold degenerate Landau levels. What's actually seen in experiment is you see every single integer with a temperature scale set by the Coulomb interactions. So really it's analogous, just like the spinful case, where the idea is that you see odd integer quantum Hall effects here coming from spontaneous symmetry breaking in the spin and valley space. But when you have spin and valley, there's actually a richer set of orders that could arise. So for instance, what I'm going to focus on here is a symmetry breaking that occurs if you fill 2 of the 4 Landau levels. So one thing you could imagine is that you spin polarize it, but fill both valleys, or you could valley polarize it, fill both spins, or you can do even crazier things. You could put one electron into a coherent superposition of the 2 valleys with some relative phase phi, and then the other electron into the same thing, but with spin reversed. These states are very interesting, and it turns out that's actually what's going to show up. So I'm going to focus on them. And we call them intervalley coherent because spontaneously you've developed quantum mechanical coherence between the 2 different momenta of the graphene. So, you know, I want to map this back to Skermi's original picture where I have something like an order parameter, which is my nonlinear sigma model. How do I do that here? Well, the relevant order now, it turns out, is going to be in the valley space rather than spin space. So I can introduce 2 Pauli operators for spin and valley order are just the bilinears, which tell you how you're polarized in the valley space. So there's 3 directions which are really important. If you point along the z direction, that corresponds to valley polarizing. So you fill more in valley k than valley k prime. Whereas if this emergent order parameter sits in the xy plane, that exactly corresponds to develop spontaneous coherence between k and k prime, and those are the intervalley coherent states. Now, why is this important for STM, like our ability to image this order parameter? Well, it's because the intervalley coherence is going to have a very interesting signature here. We said that the 2 valleys correspond to 2 different momenta in the crystal. So if you spontaneously develop coherence between 2 crystal momenta, that corresponds to a breaking of translation symmetry, which means physically this intervalley coherence actually corresponds to a charge density wave, or a density, a modulation in the density of the electrons, which triples the unit cell. So in STM, if we can image the density of the system, we might be able to see this tripling and detect that there's intervalley coherence. So what does this look like at a theoretical level? Well, we can just run calculations and say, if the system develops an order along these different directions on the Bloch sphere, what would the electrical charge density look like at the scale of the graphene lattice? And I'll show 3 cases here. It turns out that if you valley polarize, all the electron density lies on one of the 2 lattices of the honeycombs. And depending on whether it's K or K prime, it's one or the other sublattice. And on the other hand, if it sits at the intervalley coherence, you'll see it develops this funny charge density modulation here, which actually triples the unit cell. So this is often called a Kekulé distortion. And the particular way in which it triples the unit cell depends on this azimuthal angle that describes where you are on the equator. So we can actually make a movie of that dependence. This is as you're spinning around the order parameter around the equator, you can see the particular pattern in the charge density wave smoothly interpolates between these different configurations. Okay, so this gives us a way to use STM to measure where we are on this Bloch sphere. So what STM is able to measure is just the density of the electrons at the scale of the actual carbon atoms. So this is like real data from the Yazdani group. In this left figure here, X and Y, this is space you're looking at. To guide the eye, they've drawn on where the carbon atoms are in the honeycomb lattice, and the bright spots are where the electrons tend to be spending more time. And you can see, indeed, the unit cell is tripled and certain bonds take on a larger density. And we compare it against the theoretical curves. It gives exactly the middle picture, which corresponds to a particular intervalley coherent state. And at different regions of the sample, they can take these different pictures, and you end up seeing that your order parameter is pointing at different points. Okay, so this is how STM can measure out the nature of the spontaneous symmetry breaking. I'll show more pictures of that shortly. Okay, but our goal is not just to see that there's spontaneous symmetry breaking, as we already saw here. We want to image the presence of a Skermion and try and see that they have charge. So the trick for doing this is this graphene sample lies on some insulator, but sometimes there's a little bit of dirt and stuff in the insulator. In particular, sometimes there's a defect buried below the surface that carries a charge of 1. So what the graphene on top wants to do is it wants to rearrange its charge density in order to screen that impurity which is below it. Okay, so it basically wants to put a compensating charge above it to neutralize it. So this impurity just acts like a pinning potential where we might trap a charge above it in the 2-dig of interest. So if Skermions carried charge in this system, what you expect is that the way the defect would decide to screen itself is that a Skermion will wander over and just get stuck there because the Skermions carry charge. So once the Skermion's stuck there, you might hope that we could actually use STM to take a picture of it. And kind of amazingly, this blows my mind, this is indeed what they see. So this is STM on a very large length scale, 30 nanometers by 30 nanometers. So this includes tens of thousands of carbon atoms. And you'll see everywhere, if you zoom in on any patch, you'll find that the unit cell is tripled in some way, showing that there's some order there. But if you zoom in, so you see they've taken 4 detailed plots here with a zoom in on the right, all of them triple the unit cell, but the precise details of the picture seem to be changing depending on where you are in space. So here's what they find. At the center of the picture, there's this blob thing. That's the charge defect, which is pinning, which hopefully is going to pin the Skermion. And you tend to see that the detail in the pattern seed is somehow changing as you move around this defect. So let's analyze it more quantitatively. At each point here, we can look at the pattern and just read off how are you ordering on this valley Bloch sphere. Is it valley polarized or is it somewhere in the XY plane? Okay, so at each point in space, we can actually calculate this vector. And what you find is in the presence of the impurity, the vector makes this weird swirling pattern. Very cool. To analyze it quantitatively, it's a little bit more easily to draw some color plots. So what I can keep track of is what's the polarization along the Z direction and what's the polar angle, which describes the orientation along the XY plane. So this is just polar coordinates, basically. And in experiment, what you'll see is that in the presence of the defect, the angle of the symmetry breaking takes on this pattern here where it changes as a function of space only in the presence of the defects. That's the color being shown here. And then likewise, the polarization in the opposite direction also takes on a texture, and they're locked together in some particular way. So is this a Skermion? What we're able to do is actually run theoretical calculations where we can just ask, what would a Skermion configuration look like if you had a charge here which pinned it? What would be the configuration which would actually minimize the energy? And what theory finds is that indeed the ground state will prefer to localize a Skermion which carries charge 1. And then when we just say what is the orientation predicted by theory, we get the 2 color plots below, and we get really amazing agreement between theory and experiment. So what this shows that the experiment has actually taken a picture of Skermions in this order parameter. So we know that these Skermions, charged Skermions, exist. We know we have an experimental tool, which we can now use to detect which they're there. And we have a proposal that the highly exotic superconductivity and twisted bilayer graphene that we've all been arguing about for the last several years might be driven by this novel mechanism where Skermions can pair. So this is an exciting direction moving forward. Hopefully we can just put these elements together and show that Skermions really might be a route to superconductivity, either in twisted bilayer graphene or really other materials that have the necessary band structure. So with that, let me thank my collaborators and open up for any questions.
Thank you very much. So I think the way questions will have to work in this webinar mode is that people can just type something in the Q&A or just let me know that you have a question, and then I can call on you and ask you to speak. So I think this is a very interesting picture of what might be going on in twisted bilayer graphene. So hopefully some of our local experts and non-experts are curious about it. So let me ask one while they're figuring out the Q&A. So it's nice that you can trap one Skermion. As a thought experiment, I don't think this actually works in normal superconductors, but maybe it could work here. Can you see any signs of another nearby Skermion maybe having any sort of binding energy? Or like, now that you've been able to trap one, do you have an idea for how you might, go forward to see something about pairing?
Yeah, so, yes, these experiments, it wasn't in the twisted bilayer graphene, so we don't really expect that the pairing is there yet. What they do sometimes see that if there's 2 defects next to each other, you'll see a Skermion and an anti-Skermion next to each other, so that's cool, but it doesn't tell you about pairing. You'd probably want to engineer a system where you just get lucky that there's 2 defects. Well, actually, no, the way I would do it is the following. There'll be charged 1 defect somewhere. And then what you should do is adjust the chemical potential a little bit away from the insulator so that there's a finite density of Skermions around. If they're indeed paired, they'll always show up together. And then that pair will just sit on top of your defect, even though the defect only carries charge 1. So, if this pairing energy is really there, then it will always be lower energy to have the 2 of them bound together rather than separated. So in principle, you should be able to see it.
Great. So questions are coming in. Let me first ask Mike, then Christoph, then Hitoshi. So Mike, you should be able to talk.
Okay. Hi, Mike. That was a great talk. I was just curious if any of these kinds of effects might happen in any other 2D materials, an example being transition metal dichalcogenides. Yeah, so some of us are thinking about it, or you might even ask more generally, could you realize this in like cold atoms experiments, for instance? So I think the answer is yes. So the basic ingredients at the level of the band structure is you need systems which have 2 kind of flat bands, which carry opposite Berry curvature, which is what leads to them effectively looking like 2 magnetic fields. So that's actually kind of natural to get in various systems that have a valley degree of freedom, because on general grounds, the 2 different valleys can carry different Berry densities. So there might be other systems with valley that can also realize this. I'll mention one thing we're thinking about with Norm is how to do this in cold atoms. There was a bunch of excitement some number of years ago where people asked, well, how can you realize a magnetic field in a cold atom system? And they have these cool tricks for shaking the lattice. But it turns out when you look at it more carefully, it turns out that one hyperfine space sees a positive magnetic field, but then there's another hyperfine state which sees a negative magnetic field. They just focused on one of them, but that experiment already is actually realizing some similar physics there. So Yeah, I don't have another like condensed matter example where I immediately know that it's the case, but the topology has a particular name. It needs to be something fancy like a Stiefel-Whitney insulator. And I'm sure people like Andre Bernavig will probably be doing big materials searches to see if there's other examples besides twisted bilayer graphene which realize this physics.
Thanks.
Actually, let me call on Christoph next and maybe pick one of your questions for Mike.
All right, so thank you for a great talk. So in case of superconductors, you have vortices as topological defect of superconducting order parameter.
Mhm.
And of course, they are done by magnetic field. So do you think about analogical type of defect in case of superconducting Skermions? What's the...
Yes, so we actually think that if the Skermions do superconduct, so if they condense, it sounds super exotic, like maybe it's a completely different phase of matter than a usual BCS superconductor. But we actually think that as a phase of matter, superconductor made of Skermions is the same as a BCS superconductor. So in principle, you could deform one to the other. So once they superconduct, the description of it would still be given by, you have a U1 order parameter in the Higgs mechanism, and there'd be the same physics as vortices, just like in a regular superconductor. So yeah, that physics would be there just like with a regular superconductor. So the Skermions, in a sense, are different in that it's a different energetic mechanism for getting the pairing, even though the phase that results is still the same as a usual superconductor.
I mean, dimensions of these defects could be slightly different, right?
Well, at least the materials we've been thinking about are all in 2D. So they'd be vortices rather than vortex lines. I'm not sure what you meant by dimension in terms of.
I mean, just size or size of vortex core. But anyway.
Oh yeah, yeah. The energetics of the size could be quite different. I mean, that would depend on the superfluid density and the coherence length and so on.
And how about existence of Josephson effect in your system?
Well, there's two separate. I mean, in the actual experiments, which potentially don't have anything to do with Skermions, that's just our proposal. But superconductivity has been seen in this twisted bilayer graphene, and they've shown that there are Josephson effects. In our version of it, we think at the moment the pairing symmetry is kind of like S waves, so we don't think there's anything particularly interesting that we predict for the Josephson effects. But that's something we're working on now, whether there might be different ways that the Skermions can pair up that might give different pairing channels, which would then have different predictions for the Josephson effect.
Let me move on because I see at least two more questions I have to get to. So Hitoshi, please go ahead and ask yours.
Mike, thank you for the beautiful talk. I really enjoyed it, and the beautiful agreement between theory and experiment. That's wonderful. My question is about the Skermion statistics. So from the field theory side, you can have the Hopf term using a mapping from S3 to S2 that also gives you homotopy group. And in principle, you can get any statistics. So it could be anyons. Is there any way you can control the statistics of Skermions?
Yeah, that's a good question. So in the original integer quantum Hall effect, in the integer case, it's if you start with the insulator, it's not tunable, and you just get fermions. I think it's more complicated in the so in the SU4 case, I need to think about that. I don't think it's actually tunable in the SU4 case, as long as you demand that you're locked into the sector where the two layers are always equal and opposite. In principle, there's other fluctuations where your two layers start canting together to be more ferromagnetic. And then actually the charge of these objects changes away from being 2 and could be anything between 2 and 0. But so long as they're locked equal and opposite, then it's fixed. So I haven't thought about the statistics, but I think there's probably something similar that if you consider defects where things aren't equal and opposite, if the charge changes, I think the statistics probably change too, but I haven't thought about it.
Okay. Anyway, it's fun to think about.
Yeah.
Great, thank you. And for the last question, how about Feng Wang?
Oh, Mike, a great talk. I want to ask, like, or do Skermions exist in chain insulator with a chain number that's different from 1? For example, when chain number equal to 2. So in that case, will the Skermion have a charge of 2 and be a boson? Or
Yeah, exactly. So if you have a Chern 2 band like you've seen, and the spin degree of freedom makes a Skermion, then it would carry charge 2. So then you already have your pairing. The only problem there, I mean, that itself would be really interesting to see. You're unlikely to get superconductivity because that's a charge 2 boson, but when it moves, it effectively sees a magnetic field. And that might be kind of bad for superconductivity, just the usual reason that magnetic fields are bad for superconductivity. It's not impossible. In principle, you could still get a superconductor, but.
I see. So you are saying in that case, the elementary excitations are always bosons.
Yeah, though if you made a vortex rather than a Skermion, a vortex is like half a Skermion, that would carry charge 1. But those are usually more energetically costly. It's like there's some logarithmic confining energy for them.
Thank you.
All right, I think we better thank Professor Zaletel again. So, educational and enjoyable talk, and thanks to the audience, and we'll have another colloquium in a week or so.